So now we come to the 7th lecture in this series on differential equations, and in this 7th lecture we shall discuss one important topic, linear differential equation and its close cousin, the Bernoulli equation. So these are the two types of equations that we shall discuss in this lecture. So let's begin. So what is a linear differential equation? The linear differential equation is displayed on the slide now. It's equation 3.1, dy by dx plus pxy equal to qx, where p and q are functions on x which are defined on a certain interval I, assumed to be continuous. We assume that p and q are continuous functions defined on an interval I. And the differential equation is dy by dx plus pxy equal to qx. So let's go ahead and see how to solve this differential equation. And this is an important type of equation, and in a sense you can solve it completely. I say in a sense because although you can write out a formula for the solution of 3.1, that formula will involve certain integration signs and those integrals have to be interpreted, and whether you can solve it completely depends upon your interpretation of what you mean by completely solve it. If you're satisfied in a formula involving integrals, then that's what it is. Let us now look at the Bernoulli equation. The Bernoulli equation, I said, is a close cousin of the linear equation. What does it read? Dy by dx plus pxy equals qx y to the power n, which is equation 3.2 in the slide. These two equations go together. In fact, we shall see that 3.2 can be reduced to 3.1, which is why we study them together. Okay, so let us recall a formula from calculus, a very simple formula from differential calculus that you have studied and you have used it frequently. It is simply the product rule. If you take a differentiable function y of x and you multiply it with e to the power x, what is the derivative? It is y prime e to the power x plus y e to the power x, a straightforward application of the product rule. Now let us replace e to the power x by something more complicated. Let us replace it by e to the power phi of x, where phi is a differentiable function. And then look at the formula, d dx of y e to the power phi x will be what? It will be y prime plus phi prime y. These two club together into e to the power phi x. Again, it's a product rule. Now we select phi of x in such a way that phi prime equal to px. You see the statement written in red in the slide. We select phi x in such a way that phi prime of x equal to px. In other words, phi of x must be equal to integral px dx. Already we have an integral. Now, can you compute this integral px dx? We'll come back to that. So, select phi of x in such a way that phi prime of x equal to px. Then what do we get? We get d dx of y e to the power phi x equals y prime plus pxyx into e to the power phi x. You see that in the slides. So this slide is all about product rule with specific choices for the two factors. So now look at the last displayed equation in the slide. You see the y prime plus pxyx appearing there. So go back to the differential equation 3.1. You get y prime plus pxy equal to qx. So compare 3.1 with this last equation, d dx of y of x e to the power phi x equal to y prime plus pxyx the whole thing multiplied by e to the power phi x. So what does this suggest? This suggests that this combination y prime plus py, this left hand side of the differential equation 3.1, y prime plus py, if you multiply equation 3.1 by a certain e to the power phi x, the left hand side will become an exact derivative. That's the idea. Okay, so now what do? So this suggests that we multiply our equation 3.1 by exponential of phi of x, right? So what was 3.1 again? Dy by dx plus py equals q. So you multiply by e to the power phi x, multiply by e to the power phi x, you get e to the power phi x into y prime plus py on the left hand side. But we have just seen that that left hand side will be ddx of y e to the power phi x. That's what we have just seen. The left hand side becomes an exact derivative. So you see equation 3.5. So if you multiply the original differential equation 3.1, namely y prime plus py equal to q by x of phi x, we get equation 3.5, namely ddx of y of x into x of phi x equal to qx into x of phi x. Now it's very clear what we should do next. We should integrate 3.5. We should integrate 3.5 and we get 3.6. The y has been isolated. Y of x into exponential of phi x equals integral q of x into x of phi of x dx. Equation 3.6 in your slide. So now that will give you y of x explicitly. Namely, you divide by e to the power phi x and you recovered the solution of the differential equation y of x. So in a sense, we have solved the linear differential equation completely, but there are only two problems. We need to figure out what the phi x is. We need to figure out what the phi x is. What is the phi x? Integral px dx. So there is an integral sign. The phi x can be written in terms of an integral. And the second thing is, on the right hand side of equation 3.6, you see one more integration. So we have to perform two integrations. We must integrate px dx and get our phi. After we get our phi, we must integrate the right hand side of equation 3.6. So the problem of solving a linear differential equation involves computing two integrals explicitly. Since the exponential function doesn't vanish, equations 3.1 and 3.5 are completely equivalent. Let me remind you, what is equation 3.1? The original differential equation. What did we do to the original differential equation? We multiplied this by e to the power phi x. E to the power phi x is never 0. So you take an equation, you multiply it by a non-zero term, you get a new equation. So these two equations are completely equivalent. So equation 3.5 is obtained from the original differential equation by multiplication through a non-vanishing quantity. We multiplied through e to the power phi x, and that is never 0. So the original equation and 3.5 are completely equivalent. So there is no loss of information and there is no spurious things introduced into our solution process. They are completely equivalent. So now the question is, how are we going to find a phi x such that phi prime equal to p? Well, if we cannot, we are out of luck. Too bad. All we can then say is take phi of x equal to integral a to x pt dt. That's all we can say, nothing more. Look at the statement written in red. Phi of x equal to integral a to x pt dt. Well, remember p is a continuous function, so the integral a to x pt dt exists for any choice of a in the interval. And then the final solution would have a very ugly appearance because these integrals will be floating all over the place. And we are not able to compute this integral explicitly, and that was our problem. So if we cannot find explicitly integral px dx, we are out of luck. We have to live with it, and the final formula will involve integral signs floating around. In fact, there will be 3 of them, and it will have a very ugly appearance. And one cannot do any further with it, and the process stops here. Well, so let us assume that we can find a phi x. Let us assume that we can find a phi x, namely, let us assume that we are in a position to compute integral px dx. What is the solution? Look at 3.6. Look at the equation number 3.6 in this slide. Wherever there is a phi of x, I am going to replace it by integral px dx. Then what do you get? You get 3.7. So in 3.6, replace every occurrence of phi of x by integral px dx. Now there is one important thing that you need to keep in mind, namely you have 3 integration signs appearing in 3.7. Now you have been putting a constant of integration whenever you see an indefinite integral. So you might say that you will put a constant of integration c1 for the integral appearing on the left hand side, and for the 2 integrals appearing on the right hand side, you will put a constant of integration c2 and c3. So you will say, well, there will be 3 constants of integration floating around. No, that's not the case. The final answer should have only 1 constant of integration floating around. So the other 2 constants of integration must somehow cancel out. It must disappear. Remember, look at equation 3.7. Exponential of phi x dx on the left hand side and exponential of phi x dx on the right hand side, where phi of x has been replaced by integral px dx. Remember, 3.7 was obtained by multiplying the differential equation by a certain factor e to the power phi x, and the phi x was integral px dx. So the constant of integration that will appear when you integrate px dx should be the same on the left hand side of 3.7 as well as the right hand side of 3.7. So the constant of integration that you put for integral px dx on the 2 sides of 3.7 must be the same constant. And since the constant of integration is an additive constant, you exponentiate, you will get a multiplicative constant. The additive constant c will become a multiplicative constant e to the power c, and e to the power c is non-zero and will cancel out from both sides of 3.7. So 2 of those constant of integration have disappeared and there will only be 1 constant left. The final integration that you perform with the q term thrown in, that is the only constant of integration that will survive in 3.7. Please pay attention to this matter. Make sure that 2 of those constants of integration cancel out and the final answer has only 1 constant of integration. So it is understood that in both occurrences of integral px dx in 3.7 are identical, and so the same constant of integration would be assigned for both, and the e to the power c would be a factor on both sides and this factor would cancel out. So one can altogether neglect putting in the constant of integration when you compute integral px dx because that's going to cancel out anyway. So when you integrate px dx, don't bother about putting the constant of integration because e to the power c will cancel out from both sides. So just avoid putting the constant of integration in the first place when you compute integral px dx. However, on the right hand side of 3.7, when we compute the integral with the qx term thrown in, the outer integral in 3.7, so to say, there the constant of integration is very important. The final integration on the right hand side of 3.7, the constant of integration is very important. Well, all this may sound a little complicated, but I assure you that it's not, because when we start solving the problems, you will get the hang of it very quickly. So don't worry about it. It's not as complicated as it appears to be. Next, initial conditions. Very often you see differential equations coming in with initial conditions. The value of the solution at some x equal to x naught is specified, in which case the final integration should be done with the definite integral stick. So I advise you not to memorize the formula 3.7, rather derive it. It just takes a couple of lines each time you do a problem. Don't try to memorize formulas, rather try to derive this and follow the 3 steps. First, compute integral px dx and don't put the constant of integration. Step number 1. Step number 2, multiply the differential equation by e to the power integral px dx. This is easy step. Step number 3, perform the final integration. Okay. And if there are initial conditions prescribed, then in this third step, employ definite integrals rather than indefinite integrals. That's all that there is to it. It's very easy. There are only 3 steps. And the complication, if any, is in the computing the integrals. So let's look at some examples, some very specific examples for you to digest the matter. Alright, let's go to the first example now. Solve the differential equation dy by dx plus tan x into y equals sin x, equation 3.8 in the displayed slide. So it is dy by dx plus pxy equal to qx. What is a px function? It is tan x. So what are we supposed to do? We are supposed to compute integral px dx. What is the integral px dx? Integral tan x dx. What is integral tan x? Log secant x. There is no need to put the absolute value because secant function is positive on the interval in question. So the absolute value sign can be avoided because secant is positive. So integral px dx is log secant x. So e to the power integral px dx is secant x. That's easy. We have ignored the constant of integration, observe. So we have completely ignored the constant of integration as mentioned earlier. So now what is the next step to do? Multiply the differential equation 3.8 by whatever we have just obtained, namely secant x. What happens to the differential equation? 3.8 becomes secant x dy by dx plus secant x tan xy. That's the left hand side. But that is exactly the derivative of y secant x. That's the next display in the slide. Right hand side, of course, is secant x into sin x, that is tan x, whatever it is. So what has happened to equation 3.8? It has transformed to ddx of y secant x equals tan x. After multiplying by x of integral px dx, equation 3.8 goes over to the second last displayed equation, ddx of y secant x equals tan x. Simply integrate. So y secant x will be equal to integral tan x. Now we have to put the constant of integration. Integral tan x is log secant x plus c. And then you isolate the yx and you write y of x equal to cos x into log of secant x plus c. That's easy. The integrations were easy, and observe where we ignore the constant of integration in the first step. When you're integrating px dx, we ignore the constant of integration. The final integration that we perform involving the right hand side, the qx thrown in, the constant of integration has been put. That's 3.9. So that's a solution of the differential equation. Let's take an example which appeared in JEE 2011 in paper 1. I have reworded the question slightly, and I have also changed the notation somewhat so that it is in sync with what we are doing here. So what is given to you? It's given to you that y of x is a continuous function on the open interval 0 infinity. In the original paper it says y is a differentiable function. I am just saying y is a continuous function defined on the open interval 0 infinity. And what does it satisfy? It satisfies equation 3.10. Calculate the value y of 2. Now you might wonder, I don't see any differential equation here, you might tell yourself. You would say equation 3.10 is not even a differential equation. But we will soon see a differential equation appearing out of 3.10. First of all, y of x is given to be continuous. So if you take a continuous function and you integrate it from 1 to x, you are going to get a differentiable function. The integral is meaningful because y is continuous. So the symbol 1 to x yt dt makes perfect sense. Now, if you take any continuous function g of x and you compute integral of a continuous function from 1 to x, the result is going to be a differentiable function. So, integral from 1 to x gt dt is going to be differentiable with respect to x. And what is the derivative? The derivative is going to be g of x. That is the fundamental theorem of calculus. That's the fundamental theorem of calculus. So the left hand side of 3.10 is the integral of a continuous function from 1 to x. So the left hand side of 3.10 is automatically a differentiable function. So left hand side of 3.10 is differentiable, therefore the right hand side is also differentiable. And the x cube term on the right hand side is obviously differentiable. So the first term 3xyx is differentiable. Therefore, y of x is also differentiable. There is no problem. So you don't have to say in the hypothesis that yx is differentiable. It is enough to say that y of x is continuous, because equation 3.10 would force y to be differentiable. Next, we should differentiate 3.10 with respect to x and appeal to the fundamental theorem of calculus. The left hand side becomes 6 times y of x. The left hand side becomes 6 times y of x. On the right hand side of 3.10, you will get many terms. You will differentiate 3xyx using the product rule, and you will differentiate the x cube term. What happens? You get a differential equation. Notice I told you that out of 3.10, you are going to produce a differential equation, and here it is, y prime of x minus y upon x equals x. It's a linear differential equation with p of x equals minus 1 upon x. If p of x is minus 1 upon x, x of integral px dx is x of minus log x. X of minus log x, which is 1 upon x. Okay. So we must multiply the differential equation by 1 upon x. Step 2. Step 1 is over. Step 1 is integral px dx, that is minus log x, computing x of integral px dx, that is 1 upon x. Step 2 is what? Multiply the differential equation by whatever you have just obtained. Namely, multiply the differential equation by 1 upon x. So what happens to the differential equation? 1 upon x y prime x minus y upon x squared. And that is exactly the derivative of y upon x. So 3.11 d dx of y upon x is what the left hand side would become. Right hand side is 1 because you had an x and you multiplied by 1 upon x, and so the right hand side has become 1. So 3.11 is an innocent looking equation. You must integrate 3.11 from 1 to 2. What do you want? The question asks you for the value of y of 2. So you must employ definite integrals. Now if you stare at equation 3.10, there is a specific value of x which is very interesting, namely x equal to 1. So if you put x equal to 1 in 3.10, what happens to the left hand side? The left hand side straight away becomes 0. What happens to the right hand side? The right hand side becomes 3y minus 1. So 3y minus 1 is 0. So y is 1/3. So when x is 1, y is 1/3. So you got your initial conditions. Y of 1 equals 1/3. So the value of y is 1/3 when x is 1. You have been asked to find the value of y when x is 2. So what should you do? You should integrate 3.11 from 1 to 2. You should integrate 3.11 from 1 to 2, and you get y of 2 by 2 minus y of 1 by 1 equal to 1. From that you will get the value of y of 2, and that completes the problem. It's a pretty easy problem. Let's move on to the next problem. Again, I had taken a JEE question which appeared in 2014 in paper 2. The differential equation is dy by dx plus xy by x squared minus 1 equals x to the power 4 plus 2x upon square root of 1 minus x squared, and initial conditions are given to you. Y of 0 is 0. And the solution of this differential equation with this particular initial condition is denoted by f of x. What does the question ask you to determine? It asks you to determine the integral of f of x from minus root 3 by 2 to root 3 by 2. So the question is asking you not for the solution, but for the integral of the solution over a certain interval. Again, 3.12 is a linear differential equation. It's a linear differential equation. What is the p of x? P of x is x upon x squared minus 1. Remember that in some situations, your linear differential equation will not be given in the form 3.12. What they would give you is, they would give you an equation multiplied by x squared minus 1. So instead of giving you 3.12, they may give you x squared minus 1 into dy by dx plus xy equal to x to the power 4 plus 2x multiplied by minus square root of 1 minus x squared. If such is the case, then you must divide by the coefficient of dy by dx. Remember, when you do these problems, it is important to write the differential equation in the form dy by dx plus py equal to q, there should be nothing in front of dy by dx. If there is something in front of dy by dx, if there is some junk in front of dy by dx, divide by that junk and isolate the dy by dx term. So it must be first written in the form dy by dx plus py equal to q. There should be nothing else, only the dy by dx sitting there. Make sure that the differential equation is written in that form. Fortunately, 3.12 is already in that form. So what is p of x? X upon x squared minus 1. Okay. X upon x squared minus 1. So p of x is integral px dx. We have to compute integral px dx. So I have written it in a slightly different form. I have multiplied and divided by 2 for obvious reasons, and I change the sign of the numerator as well as the denominator again for obvious reasons. Remember that our differential equation is defined on the interval -1 to 1. So x ranges from -1 to 1. So what are we integrating? Minus 2x dx upon 1 minus x squared. And the integral is log mod 1 minus x squared. There is again no need to put the mod because 1 minus x squared is positive when x runs from -1 to 1. So integral px dx is half log 1 minus x squared. So what should we compute? X of integral px dx, or e to the power integral px dx. What is that? E to the power half log 1 minus x squared. What is e to the power half log 1 minus x squared? Square root of 1 minus x squared. That's what you see in the next slide. X of integral px dx equals square root of 1 minus x squared. We must now multiply the differential equation by square root of 1 minus x squared, and the left hand side, as always, will become an exact derivative, and the right hand side of equation 3.12, the 1 upon root x 1 minus x squared will go away because you are multiplying by square root of 1 minus x squared, and you are simply left with x to the power 4 plus 2x. So left hand side has become an exact derivative. So you must integrate this equation from 0 to x. So use the fundamental theorem of calculus. It will be y root 1 minus x squared minus y of 0 into square root of 1. But y of 0 is 0, remember? Y of 0 is 0. So that other term, the term coming from 0 will become 0. So you simply get f of x root 1 minus x squared equal to f of 0 plus integral 0 to x t to the power 4 plus 2t dt. F of 0 is 0. So you get x to the power 5 by 5 plus x squared. After that, you will divide by square root of 1 minus x squared. Of course, you're going to divide by square root of 1 minus x squared, but notice that you're going to get two terms. One term is an odd function, the other term is going to be an even function. The x to the power 5 is going to give rise to an odd function. Now, when you integrate an odd function from minus root 3 by 2 to root 3 by 2, the answer is going to be 0. Integral of an odd function from minus a to a is 0. The integral of an even function is twice the integral from 0 to a. You know these properties of definite integrals, and we should use that. So, you will only get integral from 0 to root 3 by 2 x squared dx upon square root of 1 minus x squared with a factor of 2 thrown in because it's an even function. The easiest way to deal with this integral is to put x equal to sine theta. Then dx is cos theta d theta. The denominator is also cos theta. The cos theta term cancels out. You simply get 2 sine squared theta d theta. How convenient. 2 sine squared theta is 1 minus cosine 2 theta. And you can easily integrate, and that's the first exercise. for you compute the value of this integral. So the JEE problems are pretty simple, it appears to me. Okay, let's move on to the next problem. JEE 2016 paper 1. So with some notational changes, the differential equation is given on 0 infinity and it reads y prime equals 2 minus y of x upon x. Remember that the minus yx upon x should be brought on the left hand side. Always rewrite the differential equation as dy by dx plus py equals q. That's the first thing to be done, and I already done that in the solution process. That's the first thing I done, is to bring the yx upon x to the left hand side. And you can see that p of x is 1 upon x and integral px dx is log x and x of log x is x. So you are supposed to multiply the differential equation by x. And the left hand side becomes an exact derivative. It is a derivative of x into y of x. Right hand side is of course 2x. Okay, so now no initial conditions are given. Okay, so let us take some convenient point on 0 infinity. Take the point 1, take the point x equal to 1 just for simplicity, and let us give some value. Let us assume that y of 1 is a, where a is some real number. So we got this equation ddx of xy equal to 2x. We got this equation ddx of xy equal to 2x. Integrate it from 1 to x. Integrate it from 1 to x and you use the fundamental theorem of calculus. Xyx minus y of 1. But y of 1 is a. So what do you get? Xy of x equals a plus integral 2x dx from 1 to x. So it's x squared minus 1. So the last display gives you y of x will be a upon x plus x squared minus 1 upon x. So you divide by x. So what do you get? Y of x equal to a upon x plus x minus 1 upon x. And then you proceed to calculate the limit of y prime of 1 upon x, xy of 1 upon x, x squared y prime of x using the last display in the slide. And I would like you to calculate these limits and answer the question. Now notice that if a equal to 1, then the right hand side simplifies, right? Xyx equal to x squared it will become if a happens to be 1. And the x will cancel out and you will get y of x equal to x. On the other hand, if a is not equal to 1, then what happens? When a is not equal to 1, then y of x will be a minus 1 upon x plus x. The plus x term is not a problem because it's going to be bounded on 0 to 2, but a minus 1 upon x, what happens to it as x goes to 0? As x goes to 0, it will either go to plus infinity or it will go to minus infinity depending on the sign of the term a minus 1. So if you look at the question in the original paper, it says f of 1 is not equal to 1, that is a is not equal to 1. Now you understand why that exception has been made in the original question paper. So that's why I written it as a comment in this slide that if a equal to 1, the solution is bounded on 0 to 2, otherwise the solution becomes unbounded as x approaches 0. Take the next question. For the differential equation dy by dx plus 2xy equals e to the power minus 2x squared upon 1 plus x squared. Is it true that all solutions have a limit as x tends to plus infinity? How would you go about doing this? It's a linear differential equation. What is px? 2x. What is integral px dx? X squared. And e to the power integral px dx is e to the power x squared. So what are you going to do? You're going to multiply the differential equation by e to the power x squared, right? You're going to multiply the differential equation by e to the power x squared. You're going to get d dx of y e to the power x squared on the left hand side. So let's see how to do this problem. So this is a given differential equation, dy by dx plus 2xy equals e to the power minus 2x squared upon 1 plus x squared. It's a linear differential equation. What is your px? Px is 2x. Integral px dx is x squared. So exponential of integral px dx is exponential of x squared. What's the next step? Multiply the differential equation by e to the power x squared. If we do that, what are we going to get? We are going to get equation 3.14 prime. The left hand side, as always, will become an exact derivative. The left hand side of 3.4 after multiplication by e to the power x squared will become d dx of y e to the power x squared. What happens to the right hand side? The right hand side, of course, becomes e to the power minus x squared upon 1 plus x squared. What's the next step? The next step would be to integrate 3.14 prime. So we do that. We could integrate both sides, but there is one small problem. The integral on the right hand side cannot be computed in closed form. You cannot calculate the indefinite integral of e to the power minus x squared upon 1 plus x squared explicitly. So what do we have to do? We have to settle for definite integrals. Alright, that's all we can do. We must use definite integrals. So let's do the following. Let us integrate both sides of equation 3.14 prime over the interval 0x. And what do you get? Use the fundamental theorem of calculus. What do you get? When you integrate a derivative, use the fundamental theorem of calculus. You're integrating what? You're integrating d dx of y e to the power x squared. So what do you get? You will get y e to the power x squared minus the value at 0, y of 0. Right hand side is the integral from 0 to x e to the power minus t squared dt upon 1 plus t squared. Okay, a little rearrangement will give you y of x equals y of 0 exponential of minus x squared plus exponential of minus x squared into integral 0 to x e to the power minus t squared dt upon 1 plus t squared, which is equation 3.14 double prime, which is displayed in the slide. Now we must pass to the limit as x goes to infinity and see what happens. The very first term on the right hand side of 3.14 double prime, which is written in red in this slide. Y of 0 is a constant and e to the power minus x squared goes to 0 very rapidly. So this term, the first term, y of 0 e to the power minus x squared goes to 0. Now, let us take a look at the second term. Okay, what is the second term? E to the power minus x squared into integral 0 to x e to the power minus t squared dt upon 1 plus t squared. Let's see what happens to this. We know that e to the power minus t squared is less than or equal to 1 for all t. But no matter what your t is, t squared is positive. So e to the power minus t squared is less than or equal to 1. So what do you get? You get the inequality 0 less than or equal to e to the power minus t squared by 1 plus t squared less than or equal to 1 upon 1 plus t squared. So integrate, what do you get? Integral of e to the power minus t squared dt upon 1 plus t squared, which is non-negative, is less than or equal to integral 0 to x dt by 1 plus t squared. Everybody can integrate the second integral, which is tan inverse of x, and everybody knows tan inverse of x is less than or equal to pi by 2. So what do we get? We get, after multiplying by e to the power minus x squared, what do we get? 0 less than or equal to e to the power minus x squared integral 0 to x e to the power minus t squared dt by 1 plus t squared less than or equal to pi by 2 e to the power minus x squared. The rightmost thing, pi by 2 e to the power minus x squared goes to 0. So by sandwich theorem, the integral term in the middle also goes to 0 and our job is done. Namely, both terms on the right hand side of 3.14 double prime go to 0 as x goes to infinity, and we have answered the question that has been posed. Is it true that all solutions have a limit as x tends to infinity? Yes. Not only that, we know that that limit must be 0. All solutions actually go to 0 as x tends to infinity is what we have actually established. Notice that we have reached a stage where we cannot compute the integrals explicitly. Integral e to the power minus t squared dt upon 1 plus t squared 0 to x. This integral cannot be explicitly computed. The final answer has to be written as a definite integral. Okay, now let's come to this Bernoulli equations. This is a Bernoulli equation, is this equation 3.15 that is displayed in the slide. dy by dx plus pxy equals qx y to the power n. It's a close cousin of the linear equation. Px and qx are continuous on the interval I. Well, what is the relation? I said we are going to reduce the Bernoulli equation to a linear equation. First of all, if n is 0, then the right hand side is simply qx. It's a linear equation already. There's no need to reduce it. If n is 1, then bring the qx term also on the left hand side and write it as dy by dx plus px minus qx into y equal to 0. That's a linear equation again. So these two cases, n equal to 0 and n equal to 1, are uninteresting because they have been subsumed in the linear case already and the discussion is over. So now to carry the discussion further, let us assume that n is different from 0 and 1. So let's assume n is different from 0 and 1, and so now let us divide by y to the power n and write 1 upon y to the power n dy by dx plus px into y to the power 1 minus n equals qx. The right hand side has been isolated. Now what next? If I put u equal to y to the power 1 minus n, then 3.15 becomes a linear differential equation. Let's see how that happens. We divide by y to the power n. We divide the differential equation 3.15 by y to the power n. And what do we get? We get 1 upon y to the power n dy by dx plus px y to the power 1 minus n equals qx. Look at the term in red. Now put u equal to y to the power 1 minus n so that du by dx equals, using chain rule, 1 minus n y to the power minus n into dy by dx. So you compare the two terms in red in the first displayed equation and the second displayed equation. Obviously, from the second equation, we are going to substitute into the first equation. So what happens to the differential equation? The differential equation transforms into 1 upon 1 minus n du by dx plus pxu equal to qx. Now you multiply by 1 minus n and lo and behold, we got a linear differential equation. Also, let me recall you that we have assumed n is not equal to 1 and we assumed n is not equal to 0 because in these two cases the differential equation 3.15 would already be linear and there is no need to transform the differential equation. So we see how to reduce a Bernoulli equation into a linear equation. Alright, and a word of warning is seen in this slide in red. We are assuming that y of x is not 0 because we are dividing by y to the power n. So if n is positive, we are dividing by a positive power of y, and so if y of x is 0, we are going to be in trouble. So we are going to make an assumption that y of x is not 0. Suppose you are given initial conditions such as y of x equal to 0, then we can't use this method. So you see, the Bernoulli equation can easily be reduced to a linear equation. So let's take an example. Let's take an innocent looking differential equation, dy by dt equals y into 1 minus y of 0 not equal to 0. Solve it with the method of separation of variables and solve it as a Bernoulli equation. So what is the equation? Dy by dt equal to y minus y squared. The condition y of 0 not equal to 0 allows us to divide by y squared. So you divide the differential equation 3.16 by y squared and you get minus y prime by y squared plus 1 upon y equal to 1. So that's a nice innocent looking equation. Now you put 1 upon y equal to u. If you put 1 upon y equal to u, then minus y prime by y squared is du by dx. So the differential equation transforms to u prime plus u equal to 1, whose solution can immediately be done because that's a linear differential equation. You solve the linear equation and you get your u. What is it? U equal to 1 plus c e to the power minus x, and so you got your u, therefore you got your y. So you solved 3.16 as a Bernoulli equation. And I think you will agree with me that this is much easier than method of separation of variables. Let's take two more exercises. Solve the following homogeneous equation. 2xy dx plus x squared minus y squared dy equal to 0, equation 3.17. Now, I am asking you to solve this as a Bernoulli equation in x. Observe that 3.17 is a homogeneous equation. You already know how to solve 3.17 as a homogeneous equation, but I am asking you to solve this not as a homogeneous equation but as a Bernoulli equation. Let's see how to do that. So what's the equation? 2xy dx plus x squared minus y squared dy equal to 0. So let's write it in the form dx by dy. So you write it as dx by dy plus x upon 2y equals y upon 2x. It is the same equation as 3.17, so I called it 3.17 prime. Alright, so you see this differential equation is a Bernoulli equation in x. It has the form dx by dy plus pyx equals qy x to the power n, where n is minus 1 in this case. So how do you solve this equation? Divide by x to the power n and put x to the power 1 minus n equals u and then proceed. Do you think solving it as a Bernoulli equation is easier than solving it as a homogeneous equations? You solve 3.17 by both ways, by both methods, and you investigate. Solve the differential equation dy by dx plus 2x tan y equal to secant y into e to the power minus x squared. Oh, this looks a little scary, is it? It is. But observe that if you multiply by cos y, something happens. So what's the equation? Dy by dx plus 2x tan y equals secant y e to the power minus x squared. So what was proposed? Multiply by cos y. So when you multiply by cos y, what happens? You get this term in red, cos y dy by dx plus 2x tan y cos y sin y. And from the right hand side, the secant y cos y becomes 1. You get equation 3.18 prime. Now let's put sin y equals u. Then what is du by dx? Du by dx is cos y dy by dx. So the term cos y dy by dx has also been written in red. So what happens to the differential equation 3.18 prime? It transforms into the linear equation du by dx plus 2xu equals e to the power minus x square, and you know how to deal with that equation. It's a linear differential equation. Okay, so I think with this slide, I shall stop today's lectures.